So every time that I come here to the lecture, I try to think of something that motivates you guys. But maybe let me ask you, do you need any motivation or you have full motivation? For those who saw me yesterday, they felt bad about me, right? After that sushi meal that I had. I'm glad not many of you came to my office hours. When you eat too much rice, you know what happens to you. The blood doesn't go up there. Much better today. I thought of something here. Some of you thought that earlier that we spend, in fact, some of you told me you spent time on something that the book did not spend much papers on, rather than time, right? But you know, the people who write the book, they write, they act as if they were the God of the universe, right? They start from what? From A, and they cover everything that there is to be known until they cover even light. Optics is covered in the book. Do you really believe that someone is an expert in all of this? So you talk to the physics folks here, you cannot find an expert in everything, right? Even profs in physics here. Of course, profs in electrical engineering is a different story. They're experts in nothing. No. Ooh. But so one of the most important laws in physics is Faraday's law. How many pages were given to that in the book? 3. Can you believe that? The plant, Tesla is planning to build a plant in Buffalo, I believe, or somewhere thereabout, to build batteries. They're expanding. They're going to have electric cars. Imagine the effect of having electric cars on our environment. Incredible. It's based on what? How are you going to charge these cars? Here they're thinking of having you park somewhere. Let's say you go to Walmart and you leave your car outside while you're shopping at Walmart. You come out and the car is fully charged. How will that take place? Through induction, through Faraday's law. How are we communicating the wireless revolution, so to speak? Faraday's law. Who's using Coulomb's law? Right? Who's using what is giving some of you headache, the potential? Right? By the way, I'm going to perhaps dedicate a lecture on potential if you guys like me to do so, because I notice some of you have some struggle with. If not, there's no need. But do you see that? Don't think that if a book gives 2 pages to something, it means that it is not important. Absolutely not. You can't make a correlation. So a question to you, as I was coming in terms of motivation, I'll just write it here and then we'll start with our lecture, is that if you have a copper, raw copper, you dig it from a mine and you put it here. Is there any energy in that copper? Who said yes? Why? Okay, good. Atoms are vibrating. So how can I bring the vibration down? Please.
Drop the temperature.
Good. How low can I drop it?
Just above absolute 0.
Okay, I think, if I'm not mistaken, Caltech managed to do that, right? To bring the temperature of some atoms, I believe hydrogen, to almost 0. They couldn't get to 0. So it was like 0 point something Kelvin. Yeah. And it's interesting, I should tell you guys, one of the pioneers in doing this was a student right here. And he did a co-op in my group. Absolutely. And he's right now a prof at Stanford. He's a young guy. I gave you too much clues to figure out who he is. One more clue. He's the son of one of the profs who are here. Okay? So, all right. So if you do that, you cut the vibration down. Let's say I go to 0 Kelvin. Is it going to have 0 energy or not? Still no. Why? Okay, so what does this mass have to do with energy?
Inductance? Somehow.
Just because we're talking about inductance. Smart. Smart try. He correlated, our lecture with assume that I end up to 0. Did you see that very nice experiment by that famous prof at MIT, the wheel turning momentum? You studied that in 105. You take a loop and you flip it hard, and then balance it on one axis, on one side of the axis. The wheel will not drop. Angular momentum. So there's a lot of spin. Where did that spin come from? Go to the YouTube. It's very, very instructive. He pushes that wheel against a motor. So the motor is giving it that spin, right? But he waits a little bit. He waits for a few minutes. Guess what? It stops. So here what's happening is that this lump of copper or gold or aluminum, there are electrons there. The electrons are doing what? Spinning. So the electron is spinning like this. It creates what? It creates a magnetic moment. But also the electron is spinning on its axis, just like the Earth is spinning on its axis. So imagine the electron spinning like this, right? Of course, in a quantum world, it's not that circular motion. It's much more complex. But the fact of the matter is that it's spinning. Where is it getting that energy from? Have you ever thought about this before? Anyone has thought about this before or not? Is that an interesting question to think about it or not? Is it? So it means that here's a system that has energy. It's turning, but it appears that I'm not giving it any energy, right? Here's the copper in my hand, but all the electrons are turning. It's a very simple question. I don't have the answer for it. But if we don't have good questions, we cannot have good answers, right? If we don't have good questions, we cannot have good answers. So before we answer a good answer, we need a good question, okay? So that's why if you go to these perpetual motion machines on YouTube, don't dismiss everything you see. Some of it is hoax. Some of it is completely hoax. Others are not, okay? So there's much more to be done to really understand how energy is coupled. So the principle that we learned way back in physics, the principle that I cannot, if I have a system, I cannot produce energy out of it without putting energy into it. I'm not disputing that. But the question is, am I pumping energy into those atoms that are flipping forever, right? Something to think about, okay? So I'm not exaggerating when I say that what we teach you is a bit artificial. I'm not shy of saying that. Other professors will not say that. So what we're teaching you is artificial. It's not wrong. It's a bit artificial in the sense that there are many layers of electromagnetics. I can give you one perspective, but there's a deeper perspective, and there's a deeper one, and there's a deeper one, okay? So that's why we cannot answer all the questions with the perspective that we have in this course, okay? That does not mean what we teach you is wrong, no. But it is not the complete picture. It's not the complete picture. So I'm going to define inductance. And inductance is one of those mysterious things. I'm going to start where we left off. So remember, we had a voltage source here. A voltage source, it does not have to be sinusoidal, but it is time varying. So this voltage source is a function of t. And then I have a wire I'm creating a loop. And then what will we end up with? We end up with a current that comes out of this, okay? That this current will be affected by the flux that pierces this loop, okay? That pierces this loop. So we said that if you want to minimize the flux, then you go and take your voltage source and try to create a smaller loop as possible, even if you have to squeeze the wires next to each other. Okay? All right. Now, we cannot do too much. There's a limit to what we can do because there's propagation. We're going to talk about propagation later on. But I can model this. I can model this circuit, this one right here, as a voltage source, and I take the entire resistance in this loop and I model it as an R, and then I have something that represents that difference in current between having flux or no flux. Okay? So we said last time that the current that comes out is going to be different because of the flux. Okay? So to move fast, I will represent that the effect, one more time. I will represent the effect of the flux as something we call inductance. We use the symbol L for it. Okay? L. So this is my voltage here. This is the entire resistance in that wire. Okay? And the resistance, what does the resistance depend on? Depends on the material property and what? And the length and the cross section. When we went to the capacitance, what did the capacitance depend on? Geometry. And what else? And the material property. Look at the parallels. Resistance depends on the material property and the geometry. Capacitance depends on the material property. Remember the epsilon naught? The permeability and the geometry. Inductance, I would expect the inductance to be dependent on the medium property, not material property, medium property. Why medium property? Because the flux travels where? In the medium. In the case of the capacitance, the potential is related to the E. Where does the E travel? In the capacitance medium. In the case of the resistance is based on current. Where does the current travel? In the wire. So we needed the properties of that wire. So here, the medium, this is the flux. The flux is going through this loop. Okay? So I expect, just expectations so far, expectations. I expect that this new thing, we called it L, inductance, is related to the medium property, which is the permeability in the case of flux, medium property and the geometry. We're not going to prove that. It's more involved. But I'm going to show you a case that you will say, that is true. But is it a coincidence? Remember, there's no such thing as coincidence in reality. There's no such thing as coincidence, okay? If you met a friend at Starbucks, and you say, oh, by coincidence, I met a friend. No, it wasn't a coincidence. That friend took several steps and walked to that place. You took several steps, and, someone who has all the physics in his mind can predict that you two will meet at that point. There's no such thing as coincidence in physics. Coincidence is just fairy tales and all that stuff. All right. So we start with, remember the EMF, this mysterious EMF? I'm going to keep repeating that word, mysterious EMF, to keep you thinking about it, okay? That mysterious EMF, which has the units of volts, is related to the time rate of change of the flux, okay, or the time derivative of the flux. It's a simple equation. Keep in mind what's implied by this equation is that this is the EMF in a loop. Which loop? The loop that defines the perimeter, or the loop that contains this flux. Clear? Very simple algebraic equation, but actually it's not an algebraic, it's a differential relationship, but it implies there's a lot of physics in it. It's loaded, in other words. Okay, so now I'm going to start hand waving. Okay? Hand waving. Do professors tell you that? No, they don't. So the flux that goes, is this? Okay. The flux that goes through a loop, B, is proportional to the current that goes through it. It's proportional to the current that goes through it, and we can write that proportionality like that. Now, someone might say, why not the flux is proportional to I squared? Okay. Based on the few things that we did, based on the very few things, what did we do? We took a line source, right? We put an I in it, and we found B. Right? Indeed, the flux going through any surface was proportional to I. That checks. Number two, what else we took? We took a loop, right? We took a loop. We found out that the flux is indeed proportional to I. So we don't have a proof, but we have evidence that that is the case. Okay? We have evidence that that's the case. So which means that the EMF, okay, is proportional to di dt. It's proportional to di dt. And the constant of proportionality, it's linearly proportional. That's when we start doing hand waving. It's linearly proportional. So which means that the EMF is minus L di t dt. And this constant of proportionality, someone long time ago called it L. You could have called it anything you wish, alpha, beta, gamma, E, F, G, whatever, but someone called it L. So this constant of proportionality is what we refer to it as the inductance. So L is defined as the inductance. Okay? Now, if there are N turns, if we have a winding we make N turns, we create a loop or N loops, we multiply this by N. Remember? We multiply this by N. Why? Because each current will give you flux. Another current, although it is the same one, right? Do you see that? The current is looping like that. It's the same current. It's not that we have two sources. But each loop, if it's DC, or even if it's not DC, each loop will contribute a flux. If you have another current, or another loop, it counts as another current. It will create another flux. So you will end up with an N here. So if we have an N loop conductor, then we will multiply this by N. Okay. So that's all. That's the inductance. Okay. Now, is it isolated at a certain point? Is the inductance isolated? No, it's not. So please keep in mind, this is a schematic. This is not physics. This is a schematic. This is a model of this reality. Before I take your question, one more time. Will this and this have the same inductance? No. Will they have the same current? No. Same argument, right? Will this and this, remember, this is the same wire. Okay, I know it does not look like it, but this is the same wire. I just deformed it. Will this have the same resistance as this? Yes. Yes. That's why inductance is a bit mysterious. One more time. This is the same one. In other words, this is 50 meters, and this is 50 meters. Will these 50 meters have the same resistance as this 50 meters? Yes. Why? Because what is the resistance depends on? You take a chunk of this, okay? This length, rho, the resistivity, and the cross-section. But the inductance of this is completely different from this. Right? So if I want to maximize inductance, there's some mathematical formulas. If you have a certain wire, okay, you can prove that a circle maximizes inductance. Okay?
So inductors are based on the inductance of an inductor is based on the coils and the size of the coils. That's it.
It's based on the geometry. That's a critical important piece of information. It's based on the geometry of what? It's based on the geometry of the wire. You want a bigger, more authentic answer? It's based on the current path. It's based on the current path. So the current goes around this path here. In this case, the current goes over a different path. The inductance depends on the current path. All right? Depends on the current path. Before I give you an example, what important applications of inductance is if you have a transistor, let's say you have a transistor. You guys, I know you haven't had transistors yet, but a transistor is a switching device, up, high, or low. That's how you send logic signals in a printed circuit board. So let's say you have a printed circuit board. This is the top board. This is the bottom board. You have a printed circuit board in your computer. And this is, you're sending ones and zeros. You send them from here, 1 or 0. So this is, think of it as a switch, up or down. Okay? When you flip this, when you pull this high, you'll learn that, I assure you, when you push this, flip this high, you create a current path. So in other words, from the top to the bottom, quickly. Okay? So you expect that the voltage between this point and this point to be 0. Doesn't happen like that. Why? Because you are sucking charges. Where are you sucking them from? From a very complex circuit. You see? So I don't know the answer to this because you have to find out exactly where the charges come from. So if the charges make that loop, then you have a huge inductance. So you have a very polluted signal. You don't have a clean 1 and 0. This is one of the most difficult things for engineers, ASIC engineers and designers to understand. Because everything else we learned, capacitance and resistance is isolated. But the inductance, I need to know the current path. So some engineers are smart. They say, I'm going to put a very high capacitance here. If I have a very high capacitance here, I'm going to create a loop, very, very small loop. I'm going to shrink the inductance. This capacitor acts as a reservoir of charges. Okay? There's nothing for free. Okay, you want to cut the inductance, you put a capacitor. The capacitor acts as a reservoir of charge. Therefore, right now, when you switch high to low in a computer printed circuit board, high to low, you're going to eliminate that very, very, very annoying, actually, phenomenon, the phenomenon of inductance. Okay, so that's why instead of sending ones and zeros like this, you're going to be sending things like that. Okay, you don't want that. Okay, let's give you an example of an inductance calculations. So one of the most important, not the most important, one of the most important is the coaxial cable, because we looked at the coaxial cable. We looked at the coaxial cable and we found the resistance of the coaxial cable and what else? Resistance and the capacitance of a coaxial cable, correct? Correct me, guys, if I'm wrong, right? So what is the coaxial cable? The coaxial cable has an inner conductor and an outer conductor. Okay? The inner radius is, let's say, A, the outer radius is B. So in other words, there's nothing here, or I should say there is no conducting medium between the two copper tubes, right? You can fill it with Teflon, you can fill it with bananas, you can fill it with, not quite. Banana is a bit conductive, right? Especially when it's ripe. The more ripe it is, the conductivity increases, right? If it's not ripe, I think. All right. Why are we always talking about a coaxial conductor? I mean, life is. Do you go to printed circuit boards and you see a coaxial conductor? I don't. What's that? You don't. You will. Well, come on. Open your laptop. Open your PC. It's a multi-layer printed circuit board. Everything is printed in this world. Everything. If you're gonna do something which is not printed, the manufacturers are not interested in talking to you. Okay, from the very beginning, plan on it. Okay, that's why this company started by your colleagues, Volterra. They're printing on. They're making circuits based on what? Ink, conducting ink. You guys heard about it, right? Printing. They're not making coaxial cables. So why do we teach you coaxial cables? Because it's in the books. So what other cables that are important that we don't teach you? The printed circuit board type transmission lines. Here is something that you find on printed circuit boards. Next time I'll show you a photo of this. Okay? So this is a multi-layer. Let's say this is a 64-layer printed circuit board. Okay? Some of them are 128. Some of them 130. In what? In half a centimeter. So where is the transmission taking place? The transmission is taking place on this conductor, the inner conductor. So you can think of this as a ground plane. Think of this as a ground plane. Does this remind me of something we saw in the midterm exam when I asked you to look at the field distribution? I can ask you the same thing here. Find the field distribution for this transmission line. Right? But right now we're interested in the inductance. Did we do this? Did we find the capacitance of this in the first half of this course? No. You know why? Because it's not easy. I cannot do it analytically. So we have to use codes. We have to program it. But for this one, I can do it analytically. That's why we teach you this. Okay? But this is not as practical as this. So we come here and we want to find the inductance, L. L is this one here, right? So it is this. To complete this picture, I'm going to bring this into here. So I'm going to write it right here. So EMF equals minus L di dt equals minus d flux dt. Of course, this has to be a function of t. If this is not a function of t, we'll get 0. All right, so L is, what is L? If I integrate both of them, okay? If I integrate both, you have to take my word for it, is that L is constant. So then I end up with L being the flux divided by I, right? So I end up with with L being the flux divided by I. Now, is it intuitive to you guys that this ratio will always be independent of I? What will make this independent of I? Think, guys, tell me. What will make this ratio independent of I?
If flux is dependent on I.
Is the flux further? Go on. No, you're right, but be more precise.
It's a function of flux.
And it has to be linear function of I, right? In other words, it can be nonlinear function of I, then I cannot do that. So in other words, the flux has to be a constant multiplied by I. So the I and the I cancel. Make sense? Otherwise, I cannot have a constant here. See, so this is the interesting thing. So the flux, we've seen that thus far from the examples that I gave you, is that the flux is always a linear function of I. Is that a coincidence? No, it's not a coincidence. It can't be a coincidence. So here's my recipe right here. That's my recipe for finding the inductance of a wire, of a system like this. So is this a wire? Does this create a loop? Yes, there's an assumption here. What's the assumption? Is that there's a current that goes in this direction, I, and comes back on the outer shell. Okay? Which means that I have to have some kind of a source between this and this. Make sense? There's a lot of interesting things here. The book gives it as an example only. The book gives this important thing as a simple example. If I were you guys, I would think of 1 million questions about that example that they give in the book. Okay? The entire printed circuit board industry is based on transmission lines. And our book gives one example to find the inductance of a transmission line. That doesn't mean the book is bad. But definitely these methods of giving you these examples are really outdated. Okay? The entire printed circuit board industry, okay, multi-billion-dollar industry, is based on designing transmission lines. Okay, so if this current is going to go this way, what happens here? How can I have a loop? I don't have a loop, do I? So when you look at the example in the book, you need to ask, where is the loop? Right? Where is the loop? If I don't, where's that? I erased it. If I don't have a loop, do I have an inductance? In other words, I'll be more precise. If I don't have a current path that starts from one point, goes all the way and come back to the same point, do I have inductance? What's that? I need a loop. So if something is cut, I don't have a loop, right? If something is cut, I don't have a loop. Of course, one might say, wait a minute, this acts as a capacitance, so you can have a continuity. The book doesn't say that. For now, I'm going to assume I'm making the assumption that this current is the same as this current. How do we create that possibility? You put a load at the end. You put a load here. What kind of load? You put a resistor. You put a resistor, you put a capacitor, you put anything you wish at the end. That means that I have right now a loop. I said something. Everything I said is fine. I said something, but that looks a little bit fishy. I said you can put a capacitor. If I put a capacitor, what would happen? Huh?
The breakdown voltage would have to be great enough for the current to start flowing, right?
There will be no current. Right? There will be no current. See how many interesting things inside this simple example, right? A capacitor will not let you have DC.
Well, if there's DC, then how's there inductance?
If there's DC, that's where we're going to get. That's precisely where we're heading. If there is no DC, if I have a loop and there's no DC, can I have inductance or not? If I have no magnetic field, excellent. If I have no magnetic field piercing this loop, right?
But that's change.
Exactly. In other words, if I have no change in the magnetic flux that's going through this loop, right? And there will be no EMF. So that the EMF that we're talking about is caused by a source. Do you follow what he said? Everybody understood his question or not? Did you guys understand it or not? I need an answer. How many understood his question? One. How many did not understand?
What's the question?
Okay, so you did not. Fine. So how many? So nobody understood his question, right? Okay. So his question is, if I have here, let me give it just. I have this loop right here. I have this loop and I put a voltage source right here. If I understood you correctly, his question is, if I have a DC current in that loop, will I be creating a flux? Yeah? Will I be? Will I be or not? What's your answer? Go ahead.
There is a flux.
There is a flux. Okay. Is there a flux due to a DC current?
It's going to be a constant magnetic field.
What's that?
It's going to be a constant magnetic field, so no flux.
Right. So far, you're right. You're right. In other words, the current here will create flux. Correct? We don't have anything, we don't have any change. We don't have any changing magnetic flux here. What did we come up with? This really, your question emphasizes what I keep saying is that it's a very simple math, but there's a lot of physics in it, right? It's a trivial math. What is the conclusion that we came up with? Is there any time derivative here? Interesting, isn't it? Do you see that? Is there any time derivative here? Does the EMF show up here or not? It doesn't. Right? Which means that this is a useful way to calculate the inductance. Okay, to calculate the inductance. Its effect will be meaningful when? In other words, the inductance's effect will be meaningful only when you have a time-varying flux. Do you see that? So we're basically trying to catch our ear by turning around. Hold on a second. I want everybody to understand this because I don't want you to go to the exam and just do the math and believe. I don't care if you get 100% or not, but I don't want you to believe that you understood this if you do the math right. okay, the inductance is meaningless unless I have a time-changing flux, right? We established that. Remember the loop that I showed? If I have a DC current in that loop, I'm going to create a flux, right? But the flux is not changing, so there's no EMF, right? There's no EMF. I'm going to take just a note here to write the following. Remember when I said the following? Remember when I said I have a source, right? Voltage source. I have a loop. And there's a current that comes out of this. I asked all of you, I said, can I represent this as so? I tricked you, right? Remember when I said, can we? And some of you said yes. I said, no, we can't. Because this I here will be different from this I. Yes? Remember that last lecture? This I will be different. But if this is a DC source, what will this I be? Same as this. Right? In other words, even though there's flux here, okay, but the flux is not changing with time. Is that clear? So if this is DC voltage, I'm going to have a DC current. You calculate the R. The R doesn't matter, right? We did the R before. It doesn't matter. It's based on a DC current. You find the R in this loop. You put that R here, and you have a perfect model. So in other words, this current will be the same as this one. But if this is changing with time, this current is not this one. Okay? This current is not this one. So what's because if this is changing in time, I'm going to create a flux that is changing in time. Hence, I'm going to induce an EMF in this loop. I'm going to induce an EMF. There's an EMF everywhere, that mysterious EMF. It's distributed everywhere. So I come here and model it as a voltage drop across an inductor. Bottom line, summary, is that the math is correct. Okay, the math is correct. But what the math led to is that calculating the inductance, I need the flux changing in time, the flux divided by I. Okay, so let's do it very quickly. So I'm going to come here and say that this I is the same as that I. So my L is the flux going through where? Going in the piercing the surface between the two wires, which is this surface right here. I can take this is the simplest surface between these two wires. This is a rectangular surface between the inner conductor and the outer conductor. Think of it as a fin, the fin of a missile, just a long fin. Okay? So I want to find the entire B that goes through this surface and then divide it by I, and then I am home free. Then I have found the inductance of that system, that transmission system.
Assuming we're at DC and we have a constant magnetic field, can't you change the orientation of the loop to get a change in flux even at DC?
It will change the flux. Absolutely, but it will not create, it will change the flux, but it will not change the current. In other words, here, if I understand your question here, if I were to change the geometry of this loop, it's not going to change this I. I will be the same. But if I have a time-changing voltage, of course, it's a different story. Okay, because we create that global effect, that non-local effect, which we call it inductance.
So it doesn't it also has to depend. I also has to be a function of T as well.
To create inductance, yeah. Yes, to create it, but to evaluate it, I don't have to. The evaluation. This is evaluation, not creation. Okay? You see? Evaluation, not creation. If this is a constant, what's the inductance in this circuit? Well, there is inductance, but is it relevant to me? It's not. Do you see one more time? If this is a constant, will this circuit, the inductance depends on the geometry, right? So this circuit with this geometry and this current path has an inductance. Is it relevant to me? No. If I have a DC source, it's not relevant to me. Why? Because I care about the current that comes out. The current in DC does not depend on inductance. After all, remember from circuit analysis, J omega L, if omega is 0, what's the impedance of J omega L? 0. Right? So it's like a philosophical question. Well, if there's an inductance, why do I care about it? Well, you care about it if you have a time-varying source. Yes?
So, what's it called? If it's a DC circuit, you can always evaluate the inductance, but it'll just have no effect on the circuit.
Absolutely. Absolutely. Okay? In other words, if you might be, you could be a very heavy person, 200 pounds, unless you sit on me, on top of my head, I don't care, right? So your weight doesn't affect me. Is that a good example or a bad example? Okay.
So the inductance we calculate is the same even after it turns to AC, or is it different?
I put a current source, okay, I put a current source, and I find the flux. Then I take that flux divided by that I, DC. Right? It's a property. It's a property of the system. Okay? But whether it will affect this IT is a different story. The I depends on the excitation. So here, okay, so the entire flux for this particular wire, for this particular system, we already solved for the B in this, between the two wires. What is the B? You take this going in this direction, so it will be mu naught divided by 2 pi, I believe, 1 over r, right? With r pointing out. What's the assumption? The assumption is this is infinite. Again, we're simplifying things. Remember the capacitance, we assume that it's infinite. So we assume that this is infinite. If it's not infinite, I'm not going to get this value. We assume this is infinite. So this is the magnetic field. So I take that magnetic field and I integrate it over entire area here. So this is area here. And I divide by I. And so we will end up with the length, mu naught, divided by 2 pi. The length, let's say the length from here to here is L. L. Then I integrate 1 over r from r equals a to b. I'm sorry? I, yeah, I forgot the I, definitely. The I is here. And then when you integrate 1 over r, what do you end up with? The log, right? By the way, I noticed some of you had points taken because you did not integrate correctly. Talk to Dr. Mansour. If you're not happy, talk to me, okay? So finally, L equals mu naught multiplied by L divided by 2 pi log of B over A. Interesting. There's no I in it. Okay? There's no I in it.
Why there is an I there? I think it's canceling out with.
L, I. Someone confused me here. The original B, yes, absolutely. Okay? Thank you. Thank you, thank you, thank you.
Does it matter if I is time varying or since it cancels out? Or?
This is based on, okay, that goes back to the earlier question. I is constant. I is constant for the purpose of calculating the flux. if I have this transmission line, transmission line and I fed it with a DC source, will the inductance be relevant? Not at all. One more thing, if I have this particular transmission line and I feed it with a constant voltage source and I have a capacitor at the end or open at the end, what will I be? 0, right? Okay, so you can work with any geometry in the world that you want and you will end up with an inductance that is independent on the current, okay? For something like this, how will I find the inductance? We use numerical codes, okay? Because it's not simply, we cannot express this analytically. We can put a current here, but I need to find the flux in this area, and the flux is not uniform, okay? That's why we don't give this as an example. Okay, guys? A question? I could have done something very quickly. Yeah, because I integrate from here to here and from here to here. So I'm integrating over the area. I'm sorry? Yeah. I mean, the details of the integration, the book does it in a different way. Because this is, B is invariant with this, along this dimension, correct? So in other words, B is constant as you travel in that direction. If you travel in that direction, B decays as 1 over R. That's why we have the integration of 1 over R, with the other dimension comes out as a constant. All right, guys? I'll see you tomorrow.